Hello everyone, Oleg is here. Today I'm going to show the power of Kedro-MLflow plugin, which combines two amazing frameworks, Kedro and MLflow. MLflow is a great and well-known framework in machine learning community. It helps to simplify machine learning workflow, for example, for experiment tracking, for model tracking, for comparison of different setups, and so on. It is also very helpful for model deployment. Kedro itself is a relatively new framework which attempts to apply proper software engineering practices to the field of data science. Mainly it bases on the pipelines which execute step by step different logic, and this helps a lot to improve reproducibility. Kedro is an extremely interesting topic by itself and is going to be the core of our solution, which is going to combine Kedro and MLflow using the plugin. But we're not going to dive into Kedro or MLflow by themselves today. Kedro actually has multiple plugins. Most popular ones are even maintained by the Kedro team themselves. For example, to deploy Kedro pipelines to Airflow, or for example, it has multiple connections to different kinds of datasets so that you can store datasets in different formats like Pickle, CSV, connect to GCP, to AWS S3, and many others. Kedro-MLflow is again one of its plugins, and this is the one which made Kedro shining to me. Let's talk first about the machine learning use case, which will be the core example within our lecture. I'm going to show a use case with a problem which frequently happens even in mature teams. We're going to study Kedro-MLflow plugin on the example of so-called Spaceflights tutorial using lots of Kedro's materials. So let's look at it. Here is how the Spaceflight tutorial looks like. It is year 2160 and the space tourism industry is booming. Globally, thousands of space shuttle companies take tourists to the moon and back. You have been able to source data that lists the amenities offered in each space shuttle, customer reviews, and company information. The project goal is to construct a model that predicts the price for each trip to the moon and the corresponding return flight. Sounds a bit complicated. We are having three data sources, something about the space shuttle, something about the companies, and the customer reviews. And our machine learning task is to solve the problem of regression to predict the prices for trips. Now let's look briefly at the data. Here is the repository which I have created for this tutorial, and the link to this repository will be below. In the repository, you can find the data folder, which is a structure suggested by Kedro, again to increase the reproducibility. There are several folders according to the different stages of the data preparation in every data science project. You can create more, but this is a template which is well recommended for everyone. So let's look at the data. We have three data sets. The first one will be shuttles. You can see that this is in Excel format. And I will show you in a bit how this is processed by Kedro. What we have in the data? We have some information about the shuttles themselves. We have an idea of each shuttle. We know where each shuttle is located, and we can see multiple countries. We see some types of shuttles and like some models. We see the engine type, nuclear, plasma, or quantum. We see the engine vendor. We see the number of engines, passenger capacity, cancellation, like the policy of the cancellation policy of each exact shuttle, the crew size, a couple of binary columns, even doesn't matter much what they mean. We're not going to squeeze everything from this data science problem. This is mostly for the introduction purposes, so we're not going to squeeze every percent from the quality. And of course we have the price, which is the price of the trip to the moon and back on this shuttle. And of course, each shuttle is owned by some company. Now let's look at the company CSV. You can see again that this is another format versus the shuttles. And about the company, we know its ID, we know some rating, probably aggregated from some reviews. We know the location of the company, we know the amount of shuttles owned by this company, and also some IATA approved, which is a binary column. I don't know what's this, but I have Googled for that, so it's some International Air Transport Association. Not sure if this will exist in year 2160, but nevertheless, this is a binary feature, which may be useful for us. Last but not least, the review CSV. For each shuttle, identified by its ID, we know some collection of scores collected from some trips, and we can see the review scores rating, the comfort, the amenities, the trip itself, crew, and so on and so forth, like number of reviews. So this is already aggregated for us. We don't have to collect like averages, sums, and so on and so forth. Reviews per something, don't know what's this exactly. Probably, I don't know, the amount of thousands of reviews or maybe millions. Again, doesn't matter for us. The proper study for the data is for another lesson. This is mostly to make sure we're able to do something with this data in terms of Kedro and MLflow integration. As you may guess, we're going to deal with this data, pre-process it in some way, and then build a regression model to predict the price of each flight. Let's look at the very high-level pipeline which may be suggested for this kind of a problem. Usually data science problems are solved in a couple of pipelines. So the first one is the ETL, where we extract the data, which may be of a very high scale, and pre-process it in some way, in some generic way. And then we start with some machine learning pipeline, which pre-processes the data in the very specific way for some specific model. For example, this may be a neural network, this may be some tree-based model, this may be different kind of model, and this will require a specific kind of pre-processing for itself. So there is some experimentation phase when you try different models, different pre-processing, different data enrichment, so on and so forth. Afterwards, you create some deployment pipeline, which takes some components from the experiment and scales them using specific infrastructure for the inference, so that the new data coming to the pipeline goes to the deployment phase, where the model artifacts are used so that you can generate the predictions. This is a very high-level overview how this may be combined using Kedro and MLflow, even using Kedro-MLflow plugin. So you create two Kedro pipelines, and then one of the pipelines, the machine learning pipeline, saves some artifacts, for example, model, to the MLflow registry, and then this artifact is used during the deployment. Now let's look how this may be implemented in details. So let's start from the very left. So let's assume we have some data flow from Kafka. This may be 3 different topics for each of the data sets we talked about. And from time to time, for example, every day, we get some data dump of the historical records. So like hundreds or thousands or any other number of records, they are stored in the historical dump so that we can use them. I will use as the example the AWS setup, but this may be really anything. This may be even local storage. So then we create the ETL pipeline. ETL pipeline usually aggregates, filters, combines different data sets together using some engines. For example, this may be AWS Batch, SageMaker, or EMR if you are going to use Spark, for example. And then at the end of the ETL pipeline, which is also powered by Kedro, we'll look at this in a bit, we produce the data which is ready for experiments and may be taken, for example, by the data science team. So in the very simplistic setup, this data doesn't need any heavy computation anymore. So only model training, but nothing in terms of pre-processing, in terms of heavy filtering, heavy joins, and so on. The second pipeline is the machine learning pipeline, and it actually consists of 2 phases. So the first one is the experimentation, when data scientists are sitting and trying to pre-process the data in some way so that some model will be able to use it. And here I state this as the model predict, because actually at the very end we just pre-process the data in some way that this may be passed to the model, and the model may be from any framework like sklearn, PyTorch, or any other, and they require the input data in some format. For example, table with rows as objects, columns as features, pre-processed in some way with or without nonce, with some data types, and so on. So this is all decided during the experimentation stage. The data scientists, they train the model, they may play with the model multiple days, sprints, or whatever. And at the end of the day, they produce some artifact. This artifact is usually a model in some format, for example, pickled model, or maybe a collection of weights. This may be a matrix together with the architecture explained in some structured format, like one layer, the other layer, and so on. And this is usually stored in MLflow. I will show a bit later how the models are stored in MLflow, but we can simplify for now that this artifact looks like some explanation of what the model is, like architecture, weights, some config, some parameters, and so on. Usually this is done manually by using MLflow library or SDK for Python, for example, when you say, please log the model with these artifacts. And then usually another team is involved for the deployment phase of the project. Usually these are machine learning engineers. They are given some artifacts plus some snippets from the data scientists about how they prepare the data for the training. For example, we have filtered these rows, we have transformed the data in this way, we have removed nonce, so on. And then we triggered model.fit. Sorry, there was a typo here. So what machine learning engineers do, they take the model artifacts, they write some more or less optimized code using the same model-specific pre-processing logic, and just invoke model.predict using the artifacts stored in some registry. You may have already guessed that from what I was describing, from the classical, unfortunately well-established processes, that there are lots of potential problems in these communications. In some teams, in some processes, there may be involved even, for example, 3 teams working on each of these pipelines. So the ETL pipeline may be developed by data engineers, or sometimes called big data engineers, who collect lots of data and pre-process this in a way that data scientists can work and experiment with this data. And afterwards, after the model setup is created, the model is kind of invented or selected from some papers and other resources on the web. During the deployment phase, machine learning engineers write the optimized code for the inference and select the infrastructure for the model execution. And usually the communication between the last 2 teams sounds like, hey, machine learning engineers, here are the artifacts which we obtained, please deploy and enjoy. And not to mention lots of communication issues in this setup. A very famous and well-known problem within the field appears the problem of reproducibility. Not to mention the artifacts. So, for example, data scientists, they send you some artifacts and in a couple of hours they send another artifact. They say, oh, sorry, we found a better model, we trained a better one, so please use this one. Not to mention that without any proper registry, this will be a mess. The real problem is with the code. For example, here is some model-specific pre-processing, and this has to be exactly the same during the inference stage, while usually these 2 phases, experimentation and deployment, are conducted in different repositories by different teams, and that's why something may be really missed during the inference. For example, the data is processed in a bit different way, and that's why even the same model, which was fitted and used during the prediction stage, will not produce the same results because the data is passed in different format. Kedro-MLflow solves this via connecting the inference pipeline together with the training one tightly, so that not only the model itself becomes an executable artifact which is stored and deployed, but the whole pipeline together with the pre-processing. You can see the difference between this and the previous schema, that these 2 entities are usually developed by 2 different teams and usually are located in different repositories, and they are prone to error or disagreement between these 2 pre-processing stages for experimentation and deployment. While in this one, you can see that the model-specific pre-processing becomes a part of the model itself, and this is registered together with the model in MLflow. So not only model predict becomes a model, but the whole model pre-processing, like filtering, transformations, and so on, they become a solid model together, so that this is executed all the time when the new data is waiting for predictions. Now let's look at how Kedro represents the pipelines I was talking about in Excalibur. I have a comment for Kedro visualization. I have created multiple make comments which will be useful during this tutorial and maybe for you when you play with this. So let's see how the pipelines look like. The Kedro-viz server is started, and now we can see the whole project we have. This project has two applications, one for ETL and one for ML, and each application consists of multiple pipelines. Let's start from the simpler one, the ETL one. Kedro bases on nodes and pipelines. So the ETL application has only one pipeline, which is the ETL pipeline, and this contains multiple entities. These database icons are the datasets, and we can see that we start from the three datasets: shuttles, reviews, companies. Then we apply some pre-processing. We get Spaceflights primary table, which we're going to deal with later. What else? There are also nodes which are depicted with F for function, and we can see that the shuttles are passing the preprocess shuttles node, which is located in the nodes.py in the ETL application. We will look at it, at the code exactly which preprocesses the shuttles. The companies also go to the preprocess companies node, which is in the same file. And we can see that this node defines the inputs, companies, and the output, preprocessed companies. So these are all datasets from this ETL pipeline. We see that after some prior preprocessing, shuttles, reviews, and companies are combined together using the create model input table node. So all this information is combined so that we can look at some shuttle features, company features, reviews, so that we can predict the price for this flight. You can also see which parameters are used. For example, in the extract unseen data node, this is the place where we create some test data, which we'll use later for testing. And we can see that we pass some parameter, which is a target column, which is price. I will show this in a bit in the code. Now let's look at the machine learning application. You can see that this is pretty large. We can start from the very top to look at this in a bit more details. So we start from the spaceflight primary table, and as you may remember, this is the output of the ETL application. So spaceflight primary table, which is located in the primary folder in the Parquet format. And the machine learning application starts from exactly this table. The same folder, the same file. From this primary table, we're going to extract target, and we're going to use the parameter. Let's toggle the target column. We extract the target, which is also stored in the features. We can see the prices, which we are going to predict later. We also split the data. We split both the targets and the features, so-called features, and we see the X-train and Y-train and Y-test and X-test. So we'll look at this later when we run the pipelines in a bit more details. But what happens next? We select some training columns using the list of columns to be used. We use the number of engines, passenger capacity, crew, and so on. We're not going to use all the features because there will be like 2,000 of them. We'll use only a limited set of them. So we select the columns we're interested in. Here we're going to feed the numerical scalar on the train data, so that then we'll have the fitted scalar, which is also persisted as a fitted scalar, as an abstraction of the dataset. And then we'll be able to transform both the train data and the test data using the same fitted scalar. Last but not least, we take the scaled data, X-train scaled and X-test scaled, and we generate features. Finally, the model is trained on the train data, and for the evaluation we use the test data, which produces the metrics. The key thing in the Kedro-MLflow plugin is that it combines the training and the inference pipelines in such a way that the nodes are reused. And you can see, for example, that all these nodes are going to be used during the training stage, but during the inference stage, we're going to use only a limited number of nodes. For example, the X-test is the synonym for the unseen data, or so-called inference data. This is the data which comes to us from, for example, a raw data source like Kafka. So we select the data in the same way as we did during the training stage. We take the already fitted scalar, which was fitted during the training stage. We transform the data using this scalar, and we generate the features in the same way as it was done during the training stage. And then these test features will be passed to the model for the prediction. Let's look at the Kedro project structure. The pipelines are described in the pipelines folder, so we can see the ETL application, which consists of nodes and the pipeline itself. In the nodes, we describe several things. For example, how to preprocess company's data. We convert the IATA data into a binary. We convert the company rating into a percentage. We also preprocess shuttles. The data has two binary columns, which we convert into a binary column. And we also parse money, which in the raw format contained some $sign. We can look at this. Yeah, you can see that it originally contained the $sign, which we want to clean, and also remove the comma so that we take just float. So these were these nodes, preprocess shuttles and preprocess companies. And as you may remember, there is another stage, another node, which combines all these data points together. So you can see that the code is here, combines all data to create a model input table. So these are the nodes. These are not yet connected to each other. What connects them together is the pipeline. So Kedro suggests a pretty nice and straightforward way to define pipelines. The pipeline is executed from top to bottom, and you define nodes, each of them consisting of a function, inputs, outputs, name, some tags, and several other fields if you need them. For example, the first one to be executed is the company's preprocessing node, which inputs companies and outputs preprocessed companies. As you may remember, I have launched the Kedro visualization server, which reads the pipelines definition and depicts them here. So you see shuttles, preprocessing of them, preprocessed shuttles. Here is the preprocessed shuttles. And then this preprocessed shuttles dataset is used for the model input creation. So this again represents exactly what we have seen at the very beginning in the Kedro-viz. A very nice feature of Kedro is that it is able not only to control the versions of the code, Git is very good at it even without Kedro, so you can commit the code used for the models, but you also can commit some configs. There is another important folder of Kedro is the conf. So we're going to look at the basic config we're using within our project. The first file of interest is the catalog YAML. So this contains all the datasets we are using within this application. So for example, here we say that the companies is the CSV dataset, which is stored in the data folder 01 raw companies.csv. This helps a lot to version the datasets you used for the pipeline with some specific configurations. For example, how you read the data. If it's a complicated format like Excel, you say which engine to use to read the data. And also this is extremely helpful to persist some intermediate datasets like preprocessed data, data prepared for the model, some data splits, xtest, xtrain, and the models, of course, like fitted scalar and the regressor model. Another interesting thing right in the conf is the parameters. We have parameters for each application correspondingly, so ETL app, parameters ETL app, and for machine learning application we also have some. We will talk about them in a bit, but you can see that exactly the same parameters which we were talking about here, which are depicted with yellow or orange, they are taken right from this parameters YAML file. And they are properly registered with Git, and apart from that, they will be visible in MLflow, which we'll see later. Let's look deeper at the ETL application we have. I have a command to run the ETL application, so let's make run ETL. We can see in details what happens in the logs. Because I have Kedro-MLflow already installed, and this is mentioned in my PyProject file, you can see Kedro-MLflow is already installed. This is already able to automatically register every pipeline run as experiment in MLflow, and we'll look at it soon. You can see that this already sees my MLflow server, which I have defined in the local configuration. You can see here that this is the whole server configuration. You can use some remote server and whatever you actually want. I have just mentioned that I'm going to use the local one. And when I run some pipeline, here I have executed the ETL application, which is the ETL pipeline in our case. And this says that it found some MLflow URI. And here is the whole pipeline. We can see that we start from the loading, the data from companies, which is the first stage of our pipeline. So the first stage is the preprocessed companies node. Here is its execution. We take the companies, which is the inputs, and we produce the preprocessed companies as the outputs. And then a very nice thing is that we store the preprocessed companies as the Parquet dataset. And this happens according to the data catalog, which we have looked at previously. So you can see that the type of the dataset is Parquet and the file path is data 0 to intermediate. And this is defined in the base catalog, as we have already seen. And this is a pretty good feature to click on it using the Kedro extension for VS Code. This was task 1 of the pipeline. Then we have 3 others: preprocess shuttles, create model input table, and extract unseen data. Extract unseen data is something I created only for the sake of experiment. I will cover this during the testing stage. Interestingly is that after the execution of the pipeline, if we update the visualization application, we'll be able to see the statistics of the dataset, which is a pretty nice feature of the Kedro-viz. So you can see that after the Kedro pipeline is executed, we can see some interesting information about the shuttles dataset. We know that it has 15K rows, it has 13 columns, and its size is 1 megabyte approximately, and we can even look on how the data looks like. So ID, price, the very raw format of the data. The same for companies, the same for reviews, and again, a reminder that these datasets are in different formats. This is Excel, this is CSV, and just because we have mentioned this already in the catalog, that these require a bit different kind of processing, a bit different kind of reading of these files. This is well understood by the Kedro. We see what kind of data we generated. After the join, we have 6K rows, 27 columns. So these are all the columns we have. And these are available for our data scientists. They can play with all, they can play with less, whatever they want. The flow is theirs. And also we extract unseen data, as I have already mentioned. This is for the testing. Let's look at the machine learning application now. We can see that this is executed in the very similar way. We take the primary table, which was prepared during the ETL pipeline. We take some parameters, and then the data is split, prepared, and the model is trained. We also have some metric calculated, and now we actually can look at how MLflow integration looks like. The core part of the Kedro-MLflow plugin is a very well-automated connection between the Kedro runs, like we do here, and the MLflow. Better show than tell. Let's launch the MLflow UI and open the server. We can see that previously or recently we have executed 2 pipelines, the ETL pipeline and the machine learning pipelines. We can see when this was executed, the duration, and many other pipeline parameters. Let's look at the ETL first. We see when this was created, who has created that, the status of the pipeline, the command which executed this pipeline, and we also see the parameters utilized. For the ETL, we used only one parameter, price, while for the model training itself, we used many more, like some model parameters, split, size, the features to be used, random state, and the target column. What else we can see? As in the pipeline, we say that we are producing some metrics at the end of the training pipeline. And these metrics, as you may see when I press command, are registered as Kedro-MLflow dataset. The type field expects some abstraction from Kedro or Kedro plugins with some specific dataset type. So Kedro-MLflow has its own types which help to register metrics properly. And here is, for example, the metric of our model. So these are called experiments. We can look what else is registered when we call model pipeline run. We see the metrics, as I have already mentioned. And the most important part is, of course, the artifacts. So we can see that lots of things are registered together. We can see the fitted scalar. This is the entity which transforms numerical columns. We also pickle the features we are going to use. This is the list. And we also have the regressor itself. So this is the model pickled. Apart from that, Kedro-MLflow registers lots of different things like the model signature, the MLflow version, the Python version used, the libraries utilized, the whole environment, so on and so forth. And what we can see here is that the whole pipeline is registered. You can see that the pipeline expects 27 columns together to be provided. And why is this so? Because you may remember that we are going to select only 8 columns for the model, for the actual machine learning model, while the whole pipeline expects 27. We have originally 27 columns, and when we select the columns according to what is specified in the features, we get only 8 columns, exactly the ones we mentioned. Because we later generate some features, there will be more. So after scaling 8 columns, but after generating features, there will be 27 because we create several transformations, for example, engines, the number of engines squared, the logarithm, and so on. But let's return back to the model schema. Again, the registered artifact is waiting for the same number of columns as there were prior to pre-processing. And you can see this on the schema. So we register the whole pipeline together with the pre-processing. So that's why the input of this node is actually registered when the pipeline artifact is registered. And this is very helpful because you will not be able to mess the schema, because this schema is exactly the raw schema which comes to the machine learning pipeline, actually the one after the ETL. This is very, very frequently messed because the raw data is taken, the data scientists do lots of stuff with that, and as soon as the similar data comes to the deployment phase, there may be a mismatch, and that's why the model will be spoiled. Because usually on the MLflow, the model is registered itself without any combination with its pre-processing pipeline. There are lots of other nice features from MLflow. For example, we can compare the machine learning applications. So we select a couple, the one I have executed recently and the one I have executed previously. We press compare, and we can do this visually, and we can just look at the run details. We see when this was executed, we see which columns were triggered. Let me retrigger this in a second. So we go to the parameters, we say that we're going to use 15% of our dataset for the testing purposes. We rerun the pipeline. You can see that even if it fails, this will be registered. So this appears here immediately. And when I update, yeah, you can see that this is executed. So let's compare the last two. It shows you what changed. So during the last run, we have the test size of 0.15. Everything else is the same, and we can see that the metrics are a bit different. It's not good to compare on different test data sets, but just to give you some sense of how this looks. And this is pretty cool because Kedro-MLflow plugin gives this for you almost for free, so you don't have to register anything. For those who have worked with MLflow as a pure package, you may remember that you have to register everything. You have to say like, please register this metric, please register this parameter. And in Kedro-MLflow, this is done almost for free without any intervention from your side. And I will show you a bit later the piece of code which is responsible for that. Apart from comparison, you are also able to register models. So MLflow suggests two different tabs, one for registering experiments and the other one for registering models. So model tab contains the models which are more or less ready for being used. For example, let's say that we have conducted some experiment and we like the model a lot. We press the register model button and we select which model it is. For example, Spaceflight price predictor. And we say that we are going to register the model. Now we can go to the model registry itself, and we see that we have multiple versions of the model. This is the one which I have just added, and we can play with different things according to the best practices of MLflow. We can say, for example, validation status of the model is pending, and we can say that we are not going to remove this tag until the model is tried well. We can say that the model also has some alias, for example, challenger or champion. And let's say that we have some rollback alias for the model, which is going to be used in case something goes wrong. And of course, this will be the model with the validation status approved. We can combine multiple tags here, for example, manual validation, some business metrics approved, and so on and so forth. So altogether, they collect the information about the models we are going to use in production actually. We can look at what the model is actually used here. We can see the features which this model expects. And again, as a reminder, this is not only the model, this is the pipeline including the model itself. Another very nice news for us is that as soon as the model is registered to the model registry, we can apply model serving and deployment features from MLflow, which is pretty agnostic to everything else, while MLflow has its own kind of templates for SageMaker, Kubernetes, and whatever else you want to use for the model deployment. So as soon as the model registry has some artifacts and environment, and as you may remember, we have everything, we can press the source run and we can see all the artifacts together with the environment the model was trained in, and this whole environment will be used for the deployment. So all shown above is achieved using Kedro-MLflow plugin. Basic usage for experiment tracking, which we have looked at here, is achieved using the MLflow hook. So what it does, it translates your parameters, pipeline runs, catalog entities, datasets into MLflow abstractions. So basically, these are just callbacks during certain stages of the pipeline run. For example, we can see that before the pipeline run, it registers to MLflow the tags, the nodes executed, and we can find this here, these tags. Another example is how it stores the model itself. So it extracts the pipeline artifacts, it takes the model signature and logs it as an MLflow function by function model. And this will be visible in the artifacts panel of the MLflow. And obviously, of course, it parses the parameters. So this is the basic usage of Kedro-MLflow plugin. It uses the MLflow hook, which automatically for you registers all the experiments with all the tags, with all the parameters utilized for this exact run. This is already extremely helpful, and for that you don't have to do anything apart from just installing Kedro-MLflow plugin. But there is an advanced usage using the pipeline ML. Let's look at our machine learning pipeline in a bit more details. It is not enough just to remember what parameters and setup you used for training. It's also important to be able to use them and the same pre-processing consistently for any kind of purpose, either local testing or distributed deployment. So you can see here that we define the pre-processing pipeline, we also define the training pipeline, and of course we define the inference pipeline. At the very bottom there is a very interesting function which produces the pipeline ML. So usually Kedro uses just pipeline class, and the pipeline ML is the new construction introduced. So let's look at the function which produces the pipeline ML. There is a very interesting and important quote in the documentation. So the pipeline ML is the class which enables to link the training pipeline and the inference pipeline in order to package them in MLflow easily. The goal is to call the MLflow hook, which we were talking about, after a pipeline ML is called in order to trigger MLflow packaging. And you can see that during the creation of this pipeline ML, we say that there is our training pipeline together with the pre-processing, which consists of the pre-processing pipeline and the training pipeline. The same for the inference, and we also say the name of the input. So inside, internally, while creating the pipeline ML, it says that some of the nodes will be reused, that the training pipeline will produce some of the artifacts which have to be used for the inference pipeline, and this is what we can actually see in the artifacts. So we see that all the features are used and the desired ones will be selected internally during the pre-processing stage of the inference pipeline. So enough with the theory. This is a very high-level overview of how Kedro-MLflow plugin works. But let me show two very nice use cases which I like the most and which I consider very helpful to visualize how solid is the pipeline we register with MLflow. I have created a test which will be useful to show the whole regression inference, and for that we have to look at how we prepare the data for the testing. As you may remember, I have mentioned that I'm going to extract unseen data during the pre-processing. So here is our ETL application, and you can see that we have the full data set and we extract some unseen data from it. So the extraction of unseen data happens as the following. So we take the whole input data set, we extract 10 rows from it, and then we save this in two different Parquet files, one with features and the other one with target. And here they are. So this is the input data which we are going to use for the inference. You can see that it doesn't have any price, so there is no leak at all. We have the ETL launched on this data already, and we have the target which we expect to see. So here are 10 values close to which we are going to predict. And now let's look at our test file. So what we do, at first we define a PyTest fixture. So we say, please find two models in the model registry, Spaceflight price predictor. And you can see that this is our existing model. Please check two aliases of it, the challenger and the champion. This is pretty helpful when you have one model constantly running and the other one which you have just promoted to challenger, and you want to make sure that if you promote this one further to the champion, this will not break anything. So that's why we test two models at once. Basically, we can do this even for more, for example, for the rollback model as well. So let's assume that we have created the new model. We are going to say that this is going to be our challenger. We have just recently trained it. And what we do, we check if MLflow is able to load this whole pipeline. If it does, then we'll use this as the loaded model. So this is the URI. For each of the URIs, we check if it's alive. If it's alive, we are going to use this in the loaded model. As I have already mentioned, for the testing purposes, we are going to use the unseen data. And this unseen data, together with the model, are going to be passed to the actual test. There is one only test here. From the loaded model, we take the input schema. Input schema is captured automatically by Kedro-MLflow plugin, so it states all the features together with their types. And we expect that the input, unseen input, will have exactly the same schema as we have seen during the training stage. So this is the first part of the testing, which is very important. So we want to make sure that the data which came to us at this stage from Kafka, for example, and when we, let us use this one, and when we try to launch inference on this pipeline, the data will be of the same types, and this will fit our pipeline well. And the second part is the most brilliant, I would say. So we take the raw unseen data without any adjustments, without anything else, in the same way as it was done prior to training. Yeah, of course, I have to know that this data will be merged together, and it is going through some very, very simple ETL to merge them together. But mainly what I try to visualize here is that this is some heavy pre-processing which filters, I don't know, billions of rows into something smaller for the training. But nevertheless, this unseen data is passed right to the pipeline, so to the loaded model. And the loaded model is the whole pipeline together with the pre-processing and the model inference. And then we check that the predictions exist, that the size of the predictions is the same as the size of the data set, that the predictions are numbers. The business requirement is the predictions are not negative, because the price cannot be negative, of course. And we have a make command to execute this test. So let's look at it. And I faced a pretty obvious failure that both my models do not see the column price, because as I have already mentioned, I have split the unseen data into the data and target. My bad. And because during the training stage, the model has been exposed to the primary table at the very top. And in the very top table, you can see that the price was given. Here it is. And you can see that there are 27 columns, and then the model registry, it says that, yeah, the price has to be there. This one. So let's add the price to the data we prepare back. And we'll use only the unseen data altogether for the testing purposes. So let's rerun the ETL. Let's rerun the email pipeline. And now we can promote the new model so that it is actually used. So let's call it a challenger. We'll remove the champion for now. And let's test the model. You can see that the champion model was not found because I have just removed it. So we have only challenger. But the challenger passed. What this means is that the model was able to predict on the unseen data some numbers. The price from here will not be utilized at all because this is filtered in the model, even during the inference. So during the inference, we select columns, and from these columns we see that there is no price column, so this will not be used for the inference. We can look in a bit more details at the predictions. So let's execute the pipeline in the debug mode. And we can see the predictions. We have the array of the predictions. Let's see if they are at least somehow related to the expected ones. So here are the expected 2200 versus 2000, 2300 versus 2100. It's very high. So the fifth one is higher, almost 4K. So they more or less make sense. The fifth one is high, the sixth one is way below, also below, like 1100, 1400 and so on. Again, not perfect, but this at least follows some logic. And we can try this once again because the ETL pipeline, it splits the data randomly, so we can try this once again. So we rerun the ETL. And we can run testing once again. So we'll look at the prices. The prices are new, as I have mentioned. This is randomly sampled. Just 10 rows from the original data. The tests pass. And if we debug once again for the challenger, this should be something more or less similar to the unseen data prices. So here are the predictions, and let's look at the actual data. So the first one, 1300, 1700, 12, 18, then a bit more, 26, even more, 2700, and at the bottom something very large, like 4700, 4100. Again, not perfect model, but at least it follows some trends. And last but not least, my favorite part is the notebook. Can we use Kedro within a notebook? Yes. So let's load some extension to be able to deal with the Kedro context. So you can see here that we're able to load all the parameters we have in Kedro. For example, we see the machine learning application parameters. They are available right via the name parameters. The altogether parameters are combined. The common parameters, the machine learning and the ETL app, if you have any, they will be available. So let's go further. The first nice thing is that we're able to load any dataset from the catalog. You can see in the catalog we have shuttles, reviews, companies, and if we just say please load from catalog shuttles, we'll be able to see the dataset. It says loading data from shuttles. It's an Excel dataset. We do not say it here. this is visible from the catalog, that this is an Excel dataset. So the Excel dataset is opened and you can deal with it and, for example, prototype some pre-processing. The nice thing about that is that Kedro doesn't come up with any weird, useless data types. This is just an abstraction over some well-known types. For example, if we load companies, this just retrieves the pandas data frame, which is a very well-known and friendly framework for tabular data processing. So we can look at the head of the data, we can check what are the values in IATA column. We can see that most of them false, some of them are true, and some of them are missing. And if we read the same data set, right, using pandas, read CSV, we can see that the data is exactly the same. The same nonce, the same floating types. So it's quite clear that Kedro catalog just wraps common libraries, for example, pandas, Spark, or any other. The second thing we can do is that we can check any dataset. So not only dataset which is an input of our pipeline, but every dataset which is persisted, registered in the catalog, and then launched in the pipeline. So for example, when we see that the pipeline has produced something, like here, when we're saving data to the pre-processed companies in the Parquet dataset, this will be available. For example, model input features, we just take it and we see that we have some table with features which will be passed further in the pipeline, which is also cool. You can debug how your pipeline behaves and you can check what the values it produces. The next thing you can check is the models themselves. So you can check the scaler. As a reminder, we have a scaler in the middle of our pipeline, which is produced by the training stage. So we take the data, we select the columns, and then we fit numerical scaler on the trained dataset and then apply on the test one. And again, if this fitted scaler is persisted, and we can see that this is persisted in the 0.6 models, we can look at it. So actually, again, as I have already mentioned, this is just a wrap on some class, for example, sklearn min-max scaler. We can see what kind of features this was trained on. This was trained, by the way, on the numerical features according to the code I wrote. So this takes engines, passenger capacity, and others, and just takes the minimum and maximum values. And we can see in the training dataset that the number of engines minimum was 0, maximum was 7 for the training dataset. Passenger capacity from 1 to 20, crew from 0 to 16, and so on. How many examples has this seen? This has seen 5,000 examples. And again, we can check this out right here. So we press on the X-train, we see 5K examples. So this is what the scaler should be trained on. And we can do the same for the model as well. Kedro takes care of serializing and deserializing. So we load the regress and we see what kind of parameters were used. For example, some of the parameters may be influenced by us in the parameters ML app. Some of them are default. Here, for example, I say that fit intercept is going to be true. And you can see that the model was actually trained with fit intercept true. We see what features were used for the model to be trained. It takes the engines, it takes the log of engines, the squared number of engines after the scaling. So actually you can play with the data anyhow. We can also check the coefficients the model obtained. I haven't bothered much with the data pre-processing, but we can assume if the data is well normalized, the larger absolute values of coefficients will have a larger influence on the model performance. For example, review scores have pretty large scale, company rating, and so on, which is pretty well expected. And finally, the beautiful part is that you can execute the nodes right in the notebook. Let's assume that we have some data set, spaceflight, primary table, and we can look at the pre-processing pipeline. So we take the pre-processing pipeline, we create the pre-processing pipeline because this is the function which produces the pre-processing pipeline, and we can see on all the nodes from it actually. So if we look at the machine learning application, the top part of it will be the pre-processing pipeline. And we can see that it first extracts the target, extract target node, it splits the data, split data node, and we see what are the inputs, primary table target column, like here, and the output model input target. Here it is. And of course the name of the node, extract target node. So this is exactly the same structure which we defined in the SRC tutorial ML app pipeline. So if we look at the pre-processing pipeline, here it is, the same first node as we're looking in the demo. So what we can do with that? We can say that we're going to deal with one exact node. So let's take the second one, select training columns. It takes as an input some test data set and the parameter features and produces its test. Let's look again at the parameters, and we can look at these parameters right here in the notebook. So we call load parameters and extract the features element of it. It's a list. And actually we're able to execute this function. So we say that we're going to execute the second node, its function. Its function is the select training columns, this one. So this is the executable, these are the parameters, this is the name. So we're going to execute the function on the table from the catalog with some parameters. And here we go. So we obtain the data set so we can debug every node of the pipeline easily right here in the notebook with great visualizations. And again, to prove that this is exactly the same executable, we take the Spaceflight primary DF, already loaded with the same parameters, and we see that it produces exactly the same values as we have seen. So, what we achieve while using Kedro and Kedro-MLflow plugin? There is a great separation of concerns between the ETL and ML pre-processing. So the ETL pipeline is defined in one pipeline and the pre-processing is in the other. So this means that separate teams may work on this. This is more engineering heavy, while this one is a bit more scientific. While connection and the contract between them is pretty well fixed. In our case, we can see that the ETL application produces the Spaceflight primary table, while the input of the machine learning application is this Spaceflight primary table. And this table is defined in the catalog, so both teams may act accordingly. And even in this setup, the nodes may be moved between the pipelines if needed. For example, you can say that we as data scientists have worked a lot and we say that we're not going to change target in the future anymore, so that we suggest the ETL team to move this node to them. So we just say we remove this one and we just extract this, for example, as the last stage in the ETL pipeline, like that. Another reason for this separation is that Kedro has other integrations with, for example, AWS Batch or SageMaker. In that case, ETL and ML training pipelines use completely different infrastructure, and it's easier to keep them separated so that you have all the configurations in different repositories. The second great benefit you achieve is that you're able to deploy the models in a simpler way. Deploying the model that includes pre-processing logic reduces the need for external data processing before predictions. And as a reminder, you can see that in the testing stage, I just take the raw data in the same way as it was passed to the training, and I just move it to the prediction. So loaded model.predict, nothing else. So all the pre-processing happens inside because it was wrapped together by MLflow. So MLflow contains the artifact of a joint pre-processing with model inference. So you don't have to worry about the model pre-processing code during the deployment phase, and you can just take the artifact and move it to, for example, container, which will be executed in the cloud. So this simplification leads to a more straightforward and less error-prone deployment processes. And the main important one is the enhanced reproducibility. Encapsulating the full pre-processing and business logic, for example, if after the predictions you have some business logic, for example, rounding the prices to the nearest whole number, ensures that any data transformations applied during the training are identically applied during the inference. And this is everything I wanted to share. I will leave the link to the repository and to the resources used below. Thank you for watching.